Today's topic is permanent magnets and magnetic properties of some metals. Permanent magnets also behave very similar to what we have seen charges in electricity, static electricity. Now, if we take a unit pole, whether it is positive or negative, when it is placed in a magnetic field, it experiences certain force. This pole will experience force in a magnetic field, which is given by a quantity called force is equal to m times. M is the pole strength of this magnetic charge, and B is the field in which it is put. Now, conversely, if we take magnetic pole plus or minus, and it also generates a magnetic field. Let us say at point P, which is at a distance r, the amount of magnetic field that it generates is equal to mu naught m 4 pi r square, where m is the pole strength of this thing, or magnetic charge, whatever you call it. R is the distance between the pole strength or magnetic charge to the point where you want to find the magnetic field. Okay. Now, before we delve into more of this subject, there are certain conventions that we should be aware of, and it makes our life simple. What are these conventions? This convention is the charge could be plus or minus. Magnetic charge, if it is plus, then the magnetic field direction is this. If magnetic pole is of negative in nature, then this is the direction of magnetic field. M plus is also called North Pole. It's just a convention. And so M plus is called North Pole and M minus is called South Pole, just by convention. There is no science to it. Now, if you take bar magnet and this is south and this is north, then within the magnet, lines of force go from within the magnet lines of magnetic force go from south to north, whereas it goes from north to south outside the magnet. Okay. Now you have to be very careful. If you see this diagram, near the ends, it is still following as if it is near the ends, the direction of lines of force is still as if it is within the magnet. It takes a while, it takes some distance away from the ends before it changes the direction. So this you have to keep in mind. Absolutely within magnet, they are south to north, and farther away from magnet, they are from north to south. Travel like this. Third is north pole of magnet repel. And why is that? Because M plus itself is a north pole. So north pole will repel north pole. Just to mention it. Fourth, we will talk about Earth's horizontal component of magnetic field goes from geometric south to geometric north. What it means is, if you take this as the Earth, and if this is north, this is south, then the magnetic fields go like this. This is south, this is north. They go from the magnetic lines of force of Earth's magnetism go from south to north. Now, this you must have already seen if you used a magnet. Whenever you take a magnet and if you just hang it with a flexible cord or whatever, it rotates a while and then it will settle down. It will settle down in the same direction as north and south. Of Earth. Or if I yeah, it's okay. If this is the direction of Earth's north and south, then the magnet will align along north-south, depending upon which pole is south and which pole is north. Will align, become parallel to geometric north-south. Now, another very interesting thing is, suppose you had a coil in which there was current I flowing. Now, which phase will or simply, let's not complicate the issue. Let's take a coil. Now, this coil, if you pass current, will behave like a magnet. Okay. Now, if behave like a magnet, then it will have a south or north pole. Which one is what? The rule is, if you see the coil from, let us say, this side, face, you see the face of the coil, and if the current is flowing like this, then what we have is that face will be south pole. And if it happens to be going in this direction, then if the direction of current is anti-clockwise, then that face will be north pole. And if you see a face and see the direction of current, if it is clockwise, then that face will be south pole. Okay. Now, as we progress into the chapter, we will see that we use compasses. A compass is primarily a box in which there is a physical magnet, a small physical magnet, and to which a long aluminum pointer is attached, perpendicular to this. Now, what we should be aware is that if the pointer is pointing in this direction, actually the magnet is perpendicular to it. And when we do all our analysis, we have to see which direction this should be, and accordingly we have to set. And normally this scale is graduated into 0, 10, 90. So is this way: 90, 80, 70. All four quadrants are marked. So this fact you have to bear in mind, that the pointer that you see in the compass is not the direction of the actual magnet, compass magnet. Compass magnet is perpendicular to it. Okay. Next topic is magnetic dipole. As we see earlier, we have seen earlier similar to this is electrical dipole. And what we saw there was that an electrical dipole consists of equal and opposite charge separated by some distance. And the physical meaning of this was that in nature there are a lot of material, or the molecules exist in such a way that the negative and positive of this are bound to each other with a distance d. It's not a hypothetical phenomena. It's actually a practical phenomena, that you have two charges of a molecule or a crystalline structure or whatever separated by a distance d. Exactly similar way is the magnetic pole. In fact, in bar magnet, this is a must. And why is it so? Because if you take a bar magnet, you have to have the positive pole and you have to have the negative pole. You cannot isolate negative part of it or positive part of it, unlike in electrical field. So what happens is, you have two magnetic charges separated, and they are separated by a distance d. So a magnetic dipole is represented as mu, and it is written as m into d. where m is the pole strength and the pole strength of plus and minus will be same. They are equal and opposite. D is the distance between them, and this is called the magnetic dipole. Then if we have a current carrying loop, and if we want to represent it with an equivalent magnet, then what we can say is, if there's a loop carrying current, it will behave, it can be represented by a magnet with pole strength M and distance separated by D, because positive M and negative M will not be, is never found in isolation. They have to be together. So the equivalent magnet is a magnet with pole strength M and both the poles separated by distance D. In this case, mu we have seen earlier is the magnetic dipole, is MD, and this is equal to I times A. I is the current flowing through it, and A is the area of the loop. Area of the loop will be this area of the loop. Now, it doesn't matter whether the loop is circular or rectangular, whatever shape it is. This formula is always applicable. Magnetic dipole is always equal to I and A. And the direction of A is, if you look at the loop, if the current is flowing like this, whichever way it is flowing, what you do is you take a screw, put it perpendicular to the plane of the loop, and rotate it in the direction of the current. Suppose the current is flowing like this, you also rotate it like this. And the direction of advancement, whether it goes forward or backward, will give you the direction of area vector. Just to summarize again, you look at the loop, put a screw perpendicular to it, and then rotate the screw, or if I can draw it slightly different way, you take a screw and you suppose this is the direction of the current, and if you rotate the screw in this direction, provided this screw is perpendicular to this area, this screw which is perpendicular to the area of the loop, and the direction of the current is like this, you rotate the screw like this. So what happens is, the screw will advance in this direction, and this direction will be the direction of area vector. Okay. You take any bar magnet. You will have M positive and negative, and they are separated by distance D. Then there is a term called M, which is equal to, or I should, normally what we do is we take this distance as 2L. Then 2 this is called magnetic moment. What is magnetic moment? It is 2 times the pole strength into half the distance, or if we say it is equal to pole strength into 2L, where 2L is the total distance. Between negative and positive pole. Now next topic is what we call as potential energy possessed by a magnetic dipole. If we take any magnet, and if we immerse in a magnetic field B, then you will have two forces equal and opposite generated, which is equal to MB. And let's say if this is the theta between them, then obviously these two equal and opposite forces will generate a torque. This will try to twist it this way. This will try to twist it this way. So these two forces, these two parallel forces will always be parallel. We'll try to generate a torque. And the torque is given as M cross P. And M we had already seen, it is quantitatively equal to 2 ml, where M is the pole strength and 2 times L is the total distance between them. B is the magnetic field in which this magnet is immersed. Now if we twist this bar magnet by a small angle, then we have to do there's some work involved. And what is this work involved? This is equal to rho times d theta. And if we integrate from one limit to another, yeah. And now what is torque equal to? Torque is equal to M into B into sine theta, as per this, yeah, and d theta. So our work done is equal to M is constant, B is constant, minus cos theta, theta going from theta 1 to theta 2. Now, conventionally what we do is, we take theta 1 as 90 degrees. So our work done becomes minus MB cos theta. The other limit becomes 0. So this is what we get. At any angle theta, the work done to bring it to that place is so much. So this is also called as potential energy. Since there are two forces involved and the distance is 2L, this will be 2mb cos theta. This will be twice everywhere. Okay. So this is also called the potential energy of a dipole at angle theta is minus 2 m l b cos theta, or simply into cos theta. Sorry. Sorry to say it again. This one will be there. The reason is that dw is equal to 2 mbl sin theta, and this 2 m and l is absorbed in m. So 2 we have already taken care. So this one will be there. This one will be there. This is the actual formula wherein 2 ml is actually m. Now we have seen earlier that if we have a current carrying loop of radius a, then if we want to find magnetic field at a point P, which is d distance away, then B is given as mu naught I E square now. If we want to take this field at the center of the loop, then D becomes 0. So this becomes, if we knock off D, mu naught I A square to A cube. This simplifies to 2. Now this is for a single coil. If you have a number of coils, then we simply multiply it. So what it says is the magnetic field generated by a single coil at its own center is given by this formula, where I is the current through it, A is the radius of the loop. Now there are various positions we can use a magnet and try to find out what is the magnetic field due to various positions. One position is that we try to find out magnetic field at a point P, which is on the axis. If it is on the axis, then the field at P will be given by M mu naught D by 2 pi L square whole square. Now, distance between these two poles is 2L. So what this formula says that if you have a bar magnet whose poles are apart by 2L and has a pole strength of M, then the magnetic field at point P and the distance D we take from the middle of the magnet. Then magnetic field is given by M, and we have already seen capital M is pole strength into distance between them, which is 2L. This is the magnitude of M, mu naught D. D is the distance from the middle of the magnet to the point P, and L is half the distance between the two poles. And the direction of magnetic field will be, B will be in this direction, because positive pole will have more force in this direction compared to negative because it is further away. Negative pole is further away, so its effect here will be less compared to positive pole, which is nearer to it. Now another configuration is, instead of being on axis, what we do is we have our bar magnet here, and we try to find magnetic field at a perpendicular bisector, meaning this is also L. So totally between them it is 2L. Let's take a point P, which is at a distance D from the midpoint. Then what will happen? If I simply draw this again, or let it be this. This pole M will have the field in this direction. This being negative will have a field in this direction. Since both these points are equidistant from point P, if I say this is A, force A, and this is force B, then in magnitude force A and force will be same. And what will happen is the vertical components will get cancelled and the horizontal components will get added up. So the final B, what we get is M naught 4 pi is the final form. M is the magnetic moment, D is the distance of point P from the midpoint of this magnetic dipole, L is the half the distance of magnetic distance between the two poles, and this is the direction. And the direction of B will be, this is the direction of B. Another position is that neither we are on axis nor we are on magnetic bisector of the dipole. We are at any arbitrary distance, a position. Let us say from the midpoint, we are at any arbitrary position P. Then what happens is, this will be the direction of our B in radial direction. Let's say this is our final vector B. We can resolve it into two components. One component is along this, another component is perpendicular to this. Okay, let's say this makes an angle alpha. This is theta. Then what we do is, from here we draw another line which is perpendicular to this. This direction we call as in the direction of theta. This is in the direction of R. This B, the resultant B, we can resolve into two directions, along the radial direction and direction perpendicular to it. Okay. And let us say this angle made is d theta. And this distance is R. Then magnetic field is given by mu naught M C by R cube M. We know R is the distance between the point from the middle of magnetic dipole. Theta is the angle which the radial vector makes with the axis of the dipole. And tan alpha is given as b theta by br component, which is sin theta divided by 2 cos theta is equal to tan theta by 2. This is the angle. This is the angle of the final magnetic field generated by this dipole. Then its direction from radial vector is given by angle alpha, and angle alpha is defined as this. Well, let's talk about something about Earth's magnetism. There's a term called dip. What is a dip? We know you have Earth. And Earth's magnetic lines of force go from south to north. Now, are they horizontal or are they vertical? No. It could be in any, it could be at any direction. So, what do we want to know? We want to know if the direction of Earth's magnetic field is this, then how far, if we resolve it into two components, the horizontal components we normally call BH, what angle does it make with the horizontal? This is called dip. So and how do we measure it? What we do is this we do by help of a instrument called dip circle. This is the instrument through which we measure the dip angle. It basically is a vertical scale over which this magnetic needle can rotate. The axis of the needle is horizontal, you can see. And this whole frame is again can be rotated in the vertical axis. And how much it has rotated? There is a scale given here through which we can measure the rotation of this vertical scale. Now what we do is to measure dip angle, this plane of this instrument has to be made parallel to the plane of Earth's magnetic field. And how do you do that? What you do is you rotate this circle in such a way that the needle starts showing zero, become vertical. When the needles become vertical, at that position, you are in a plane. Suppose this is Earth's north-south. If your needle becomes vertical, then your plane is aligned to plane perpendicular to Earth's magnetic field. So in this position, this needle become vertical. Now what you do is note down this position of this hair and rotate it 90 degrees. By rotating this 90 degrees, you will align your instrument in magnetic north-south. Now your job is done. Once the dial, the vertical dial is in the field of magnetic meridian, then whatever angle it makes with the horizontal, this angle theta, it is important which angle you will take. The angle which this needle makes, this angle which this needle makes with the horizontal, not the vertical. Now the angle which this needle makes with the horizontal is called dip angle. Okay. Now next term is declination. What is declination? We know that if this is our geographical meridian, this is not same as magnetic meridian. There is a difference. The magnetic meridian, there is an angle between magnetic meridian and geographical meridian. Let us say if this was our geographical meridian and this is our magnetic meridian. then the angle between them is called declination. Is the angle between magnetic and geographical meridian. Because these two meridians are different. They don't coincide with each other. In case of dip, there is a very interesting formula, and which is that we had mentioned that you have to align, to take dip angle, you have to align this with Earth's magnetic meridian and then take the reading. Not necessary. There is another way to do it, and which is you take dip angle at any two angles. Let us say you take it at delta 1 and delta 2. Then this is the dip angle measured at position A. And if you measure dip angle at position 2, dip angle measured at position B, such that there is a condition such that B and A are perpendicular to each other. If the plane in which you measured delta 1 and delta 2, if those two planes are perpendicular to each other, then it doesn't matter where was this plane, where was this plane. There's a very special relationship, and which is, it says is cot square theta delta 1 plus cot square delta 2 is equal to cot square delta. What it says is, and this is the true dip. If you want to find true dip, it is not necessary that you have to align this magnetometer, this dip circle parallel to Earth's magnetic field. No. Take the dip angle, dip value at any two places, provided their planes are perpendicular to each other. Then this formula, through this formula, you can find the true dip. Sometimes this becomes very easy that we are not able to align this meter, this dip angle, but we know what will be if there's a plane at one angle, what it will be at 90 degrees to it. We know that if you have two forces, and if we know if they are perpendicular to each other, the resultant will lie at some angle here, making this angle. Okay. Now, if we know this angle theta, and if we know the resultant of this from one of the forces, and if we know one of the forces, then we can find out the second force by using a tan theta formula. What is tan theta here? Perpendicular over base, which is Now this principle is used in an instrument called tangent galvanometer. To measure the relationship between two forces. Okay. So how does this instrument look like? The instrument looks like this. You have a coil, electrical coil, which is vertical in your number of turns here. Then in the middle of it, you have a needle which is free to rotate in horizontal direction. You see, this magnetic coil is in vertical direction, in vertical plane, whereas the compass is in the horizontal plane. Okay. So any field that is generated in this frame due to current that is passed will be in a perpendicular direction, this way depending upon the direction of the current. Whereas this compass is moving because of field in this horizontal direction. The vertical components don't affect it because it is vertical component will have no effect on this. So what we have a case of two forces perpendicular to each other, and if we can find the resultant of this angle, then we can find the relationship between these two, right? So construction wise I've already explained. Then now what we do is, first this compass has to be made aligned to magnetic north south. Right? So what we do is we rotate this vertical frame in such a way that it aligns with the needle of the compass. So it becomes this, now this frame is parallel to Earth's magnetic field, and the field that will be produced will be perpendicular to it. So our job is done. Now what we do is, once this frame is aligned in magnetic meridian of Earth's magnetic field, we pass a known current to it. And when we pass a known current to it, the current will generate a field B, which is given by this formula. Yeah. And we know if Earth's magnetic field is BH, then what will happen? This is the B generated by electric current, and this is because of Earth's magnetism. And so if we take the angle between the two, then we know tan theta will be given by this formula. Yeah. If we write tan theta is equal to electric magnetic field because of current divided by Earth's magnetic field. And magnetic field generated by current is given by this formula. And so if we multiply Earth's magnetic field with tan theta, we get this field generated by the current. So this is an important formula. Wherein I is the current flowing through the coil, N is the number of turns, R is the radius of the coil. So this way, if we know the current, we can find BH, Earth's horizontal magnetic field, or conversely, if we know Earth's horizontal magnetic field, we can find the current flowing through this. So this is a convenient way of generating a relationship between field generated by a current vis-a-vis Earth's magnetic field. Now there are two other methods by way of which we can find magnetic strength of bar magnets. There are another magnetometers which is basically used in two positions. One is called 10A position and another is 10B position. What are these called? I'll explain. Let's take, I will briefly explain you the construction of the magnetometer. A magnetometer is basically a wooden frame, a long wooden frame in which you have the compass needle fitted into it. This frame, you can rotate it this way or that way for the adjustment purposes. And this is marked, this frame is marked 90 degrees, 0 degrees, 90 degrees, again 0 degrees. Now what you do is, 10A position is also end-on position. What we do is, we place our magnet along the axis. This is our north-south. And what we have to do, this is our Earth's north-south, east-west. We know that our magnetic field always goes north-south. So the other field has to be perpendicular to it. So what do we do? What we do is that we'll change the color here. We have learned earlier that if the compass pointer is pointing this way, then actually the bar magnet of the needle is perpendicular to it. Okay. Now, for the two fields to be, and we know that due to bar magnet, the field is actually in this direction. Now, we know Earth's magnetic field will be in this direction. So the other field has to be perpendicular to it. So to make this field perpendicular to it, what we have to do is align this magnet of the needle parallel to north-south, which means that if the magnet needle, the aluminum pointer is pointing to 0, 0, then actually the compass magnet is perpendicular to it. That's what we want to do. So this is the field of the magnet, the Earth's magnet, and this will be the field generated by the bar magnet. Now, in such a case, what happens is B, which is generated by the bar magnet, divided by BH, is given by tan theta. And we know that M by BH is equal to 4 pi tan theta is the ratio between the two fields. And what are these two fields? Two fields are field generated by bar magnet and Earth's horizontal component, because the other component of Earth is not coming into picture, because the needle can move only in horizontal plane. That being so, then this formula holds, where M is the magnetic moment of the magnet, which is also called as 2ml. M is the pole strength and 2L is the distance between the, this is 2L. Between the poles, two poles is the distance is called L. Okay. And D is the distance from the center of the bar magnet to the point where we want to make the measurements. Since we are taking the measurement at this place, we take this distance as the this distance, which is from the middle of the magnet to the center of the magnet needle, is that we are interested in, because we are trying to take the tan theta at this particular point. One field will be working like this, one field will be going like this. So this is the ratio of these two fields, wherein D is the distance between middle of the bar magnet till the center of the pointer needle. L is the half length of the distance between two poles. So this is the way to find the ratio of the two magnetic fields. Let's talk about tan B position. In tan B position, what we do is we do not align the magnet along the axis. We align it perpendicular to the axis. How is it? What we do is we have our magnetometer. This is the axis of the magnetometer, and we place our magnet like this, in this position. And again, if our Earth's magnetic field is like this, then we have to make sure that at this junction, Earth's magnetic field is this way. So the field generated by our magnet should be perpendicular to it, and which it is. We know that. We've already seen that if you try to find the magnetic field at a point which is at perpendicular equator of the magnetic bar magnet, the field is parallel to the magnet in this direction. So again, our job is done. We have a field in this direction, we have a magnetic field in this direction, and whatever angle theta which is made by this magnetometer will be will give the tan theta of the ratio of the two. So what we have to do is, again, this is the magnet of the needle of the compass. Which is aligned along Earth's northwest. If that be the case, then the pointer will be perpendicular to it. So what we do is, we first align the arms of the magnetometer along north-south, and then we place a magnet here, and this will make this rotate. And then what we do is, we take the angle theta, and mind it, we have already seen that if we have two fields, if this is BH horizontal field and this is another field which may be generated by the magnet, we always take the angle from Earth's horizontal field, because we can take this angle also, but by convention our angle is angle from Earth's horizontal field. Now in this case, our formula of this is on account of strength of the magnet, and this is on account of the Earth's horizontal field, which is given as this, again we know, is equal to m into 2L, where 2L is the total distance between the poles, and in this case d will be this distance from the center of the magnet to center of the magnetic compass. So we know d, we know L is half the distance between the two poles, and mu naught. So this is the formula if you're using tan B position. There's a small correction while defining tan A position formula. We missed out a factor tan theta. Similarly, in tan B position also we missed it out. Tan theta is multiplied in both the formulas. There's another way to find out, and this is very unique way. What if we take a magnet we tie it in the middle and suspend it by a string. and give it a slight push. What will happen? It will start. If we give a slight push, the magnet will start rotating like this, and it will execute simple harmonic motion. Okay. So what? Let's see. Does it say anything? Okay. This is 112 total length of the magnet. Then, you know, if a body is moving in a simple harmonic motion, its time period is given by 2 pi under root I by MBH. This is from simple harmonic motion. Now T is the time period of oscillations. I is the moment of inertia in this particular configuration, meaning the axis goes through the middle of the magnet while the magnet is horizontal. In this position, I is to be taken. M we know is magnetic moment, which is equal to 2L. This is the length of the magnet, distance between the two poles. This is the pole strength of the magnet. And BH is horizontal component of Earth's magnetic field. Okay. Now we will study the property of magnetic property of matters. If you take any substance, any object, put it in a magnetic field. If this object is in a magnetic field, what happens to this object? Now, depending upon the nature of this object, you may find that this object has acquired some magnetic properties. If you take out magnetic field, this may have magnetic properties. And there are certain materials, and this magnetic properties or the way it behaves like a magnet may vary from material to material. Some material may become very strong magnet, some becomes very feeble, and some maybe none. Okay. So let's see their behavior or treatment. If we define a term called I, which is intensity of magnetization, then I is equal to, where M is the magnetic dipole or magnetic moment, which is equal to, and the volume is, where is A is the area of the magnet, and 2L is the length of the magnet. More the value of I, stronger is the value of M. Meaning, this is more if I is more, we can say that this material is more magnetic. Okay. And if we knock off L from both the sides, this M2 as well. M2 we have knocked out. So it is simply the ratio between the pole strength and the area of cross section. When we are trying to let's say we are trying to magnetize this object, and the magnetizing field intensity is H, then what happens is, this magnetizing intensity is equal to the field, let's say is the body, it was immersed in field H. Then within the body there will be magnetic field generated, which is B, and it also got magnetized with the intensity I. So what happens is that the actual field generated by this magnetic substance is equal to the magnetizing field, the intensity of the magnetizing field, and the extent to which it got magnetized by the magnetizing field. Okay. Now, how much it has got magnetized will depend upon the material itself and the strength of the magnetizing field. Okay. So we know that it depends upon field of magnetization. What else? All we can say, stronger this field, more is I. Okay. So can we say I is proportional to H? Yes, it is. And what is the proportionality constant? Proportionality constant is a term called susceptibility. How susceptible is this material to get magnetized? More the value of Xi, more susceptible is this material to get magnetized. Okay. So we can write okay, or we can say Uh, we take H outside. Same thing. Now this term has a special meaning, and it is called permeability of the matter, which basically depends upon value of Xi, which is the susceptibility. The more susceptible is material, more permeability of the matter it is. We also define another term called relative permeability. Relative permeability. What is relative permeability? It is defined as the ratio of these two terms, and this we know. This is the permeability of the material, and this is the standard mu naught. And the permeability of the material we have already seen is how much? This is the permeability of the material, which is so our relative permeability is now we talk about different type of materials from magnetic properties point of view. We have basically three type of materials. One is diamagnetic material, paramagnetic material, and ferromagnetic material. Now, as a layman, ferromagnetic material are the material which gets magnetized very fast, which are magnet friendly. This is somewhere in between, but this is perhaps opposite to it. Now, if we analyze it in terms of their permeability, the value of permeability is, this lies between it is always negative, or at the most zero. It's actually always negative. Then for paramagnetic, it lies between 0 and some fixed value. And for ferromagnetic material, this is much, much larger than that. Okay. Now, what are the properties of these materials, for example? What is the property of diamagnetic material? A magnet repels material. We thought magnet attracts materials, but magnet will repel a diamagnetic material. Second is superconductors behave like diamagnetic material, because you see in levitation the rails never touch the wheels of the train, or the train never touches the wheels tracks. This is the train, it is running on the track. There's always a gap maintained. It never touches, it levitates, something like floating in the air. And why it is so? Because of this this property, that the magnetism repels this body. It doesn't attract, it repels. It doesn't come let it come close to it. Okay. And few examples are bismuth, copper, lead, silicon, nitrogen, etc. And what are paramagnetic material? They do not repel like diamagnetic material. They're somewhere in between. It weakly attracted by magnet. It doesn't repel, it is attracted, but weakly, not very strongly. Examples are aluminium, sodium, oxygen, etc. Ferromagnetic. Oh, this is our friend. It gets strongly magnetized in external magnetic field. So in motors and all other electromagnetic equipments, the core is of ferromagnetic material. And the reason is that the core becomes magnetized very fast, very easily. So you have three categories: diamagnetic, which it doesn't like magnets; paramagnetic, yes, okay, weakly it likes; ferromagnetic, very strongly, can behave as a very strong magnet. Next is what happens to does the magnetization changes with temperature? Yes, it does. How does it change? Xi is inverse to absolute temperature. This is Lewis constant. This is the same side, susceptibility. Now this formula is true till your temperature is less than some critical value. And this critical value is called Curie's temperature. Now what happens after reaching Curie temperature? Then after reaching Curie's temperature, this susceptibility is equal to some another constant divided by T minus Tc. This is Curie's temperature, which is a constant, and this is our absolute temperature of the body. So susceptibility behaves differently in different conditions. But one thing is sure, with increasing temperature, the susceptibility decreases.